Right now, you are being penetrated by something invisible, intangible, and impossible to detect directly. Not radiation, not neutrinos, dark matter. Every second, approximately 1 billion dark matter particles pass through your body, exactly as if you did not exist to them, because to them, you do not. They do not emit light, reflect light, or absorb light. They do not interact electromagnetically with a single atom in your body. The only way they acknowledge their own existence is through gravity. And gravity tells us they are everywhere. Now consider a number that forces every physicist to stop. In the observable universe, all visible matter, every star, planet, gas cloud, dust particle, you, me, every rock and ocean on Earth, added together accounts for only 5% of the total mass energy content of the universe. The remaining 95% is something we cannot directly see, cannot directly touch, and have not yet fully understood. Approximately 27% of that is dark matter. It has mass, it has gravity, it simply does not interact with light. The remaining 68% is dark energy, not matter, but something causing the universe to accelerate its expansion, something whose fundamental nature is the greatest unsolved mystery in modern physics. In other words, the physics we built over thousands of years can only describe 5% of the universe. We are essentially blind to the cosmos we inhabit. Stop and think about one question: how do we know dark matter exists? We have never seen it. We have never directly detected it. We only have indirect evidence. But that indirect evidence, layer upon layer, has accumulated into a mountain that cannot be ignored. The first piece of evidence comes from the 1970s. Astronomers Vera Rubin and Kent Ford observed the rotation speed of the Andromeda Galaxy and discovered a phenomenon that directly challenged Newton's law of gravity. According to Newton's law of gravity, stars at the edge of a galaxy should rotate more slowly than those near the center, just as Neptune orbits far more slowly than Mercury in our solar system. But the observations showed that stars at the galaxy's edge were rotating just as fast as those near the center, or even faster. This meant either that Newton's law of gravity was wrong at galactic scales, or that galaxies contained enormous amounts of invisible mass whose gravity was maintaining the orbital speed of edge stars. Systematic observations of hundreds of galaxies produced the same result. The second piece of evidence: gravitational lensing. General relativity predicts that mass bends spacetime, and light travels along curved paths through curved spacetime. When a massive object lies between us and a distant light source, its gravity bends the light from that source, producing a distorted or magnified image, like a cosmic lens. By measuring the strength of the gravitational lensing effect, we can work backward to determine how much mass produced it. The result: the invisible mass is 5 to 6 times greater than all the visible matter combined. The third piece of evidence: the large-scale structure of the universe. The universe is not uniformly distributed, it has filamentary structures, galaxy clusters, and enormous voids. Computer simulations show that if the universe contained only the ordinary matter we can see, the large-scale structure we observe today could not have formed in the universe's 13.8 billion year history. Forming today's galaxy clusters and cosmic web requires additional gravity, the gravity that dark matter provides. 3 independent lines of evidence, all pointing to the same conclusion. WIMPs, weakly interacting massive particles, have been the most favored dark matter candidates for the past several decades. Theory predicts that dark matter particles should have masses roughly 10 to 1,000 times that of the proton, interacting with ordinary matter through the weak nuclear force at an extraordinarily faint level. Why are WIMPs so favored? Because of a coincidence that excites physicists. If WIMPs exist, the residual WIMP abundance produced in the early universe's thermal equilibrium, according to the standard cosmological model, matches the dark matter density we observe almost exactly. This is called the WIMP miracle. The world's most sensitive WIMP detection experiment, LUX Zeppelin, sits 1.5 kilometers underground in a former gold mine in South Dakota. Its 2022 results: in a specific WIMP mass range, the detection cross-section upper limit reached approximately 9.2 times 10 to the negative 48 square centimeters, the most stringent constraint ever achieved. But, no signal detected. Not just LZ, over the past 20 years, dozens of WIMP detection experiments worldwide, without a single exception, have all returned zero signal. The WIMP parameter space is being systematically eliminated. The Axion was predicted in 1977 to solve a completely different problem in particle physics. It is extremely light and interacts with ordinary matter at an extraordinarily faint level. But it has a special property: in a magnetic field, an axion can convert into a photon. This provides a detection pathway. The ADMX experiment searches for the faint microwave signal produced when dark matter axions convert inside a superconducting magnetic cavity. In 2024, the Haystack experiment used quantum squeezing technology to push axion detection sensitivity below the quantum noise limit. The first time axion detection had been performed within the theoretical limits allowed by quantum mechanics. Still no signal. Primordial black holes are the most conservative dark matter candidates, requiring no new particle physics whatsoever. In 2016, LIGO detected the collision of two black holes each approximately 30 solar masses. A 30 solar mass black hole is rare in conventional stellar evolution theory, raising the question: could these be primordial black holes? If primordial black holes constitute a significant fraction of dark matter, they would produce observable gravitational microlensing events. Systematic monitoring of millions of stars in 2019 showed that primordial black holes cannot account for more than approximately 20% of the total dark matter. In 1998, two independent supernova research teams, while observing Type Ia supernovae, discovered a fact that shocked everyone: distant supernovae were dimmer than expected. Dimmer means farther. Farther means they are receding faster than anticipated. According to Big Bang theory, the universe's expansion should be gradually decelerating under the influence of gravity, like a stone thrown upward that gradually slows and falls back. But the observations showed that the universe's expansion is accelerating. Something is pushing the universe outward. That something was named dark energy. Einstein had introduced a cosmological constant lambda into general relativity, originally to keep the universe static. He later called it the greatest mistake of his life. But the 1998 discovery suggested the cosmological constant might be real. The problem: quantum field theory's theoretical prediction for vacuum energy is approximately 10 to the 120th power times larger than the observed dark energy density. This is the largest numerical discrepancy in the history of physics, known as the cosmological constant problem, one of the deepest crises in contemporary physics. In April 2024, the Dark Energy Spectroscopic Instrument released its first year of observational data, the largest 3D map of the universe ever created, covering approximately 6 million galaxies and quasars. DESI uses measurements of baryon acoustic oscillations, fixed-scale markers left by sound waves in the early universe's matter distribution, to precisely measure the history of cosmic expansion. DESI's results indicate that dark energy may not be a constant. If dark energy evolves over time, then the simplest cosmological constant model is wrong. DESI's data fits the dynamic dark energy model between 2.5 and 3.9 sigma better than the cosmological constant model. In particle physics, 5 sigma is the threshold for a discovery, 3 sigma is the level of a hint. DESI's result sits in the hint zone, not yet sufficient to overturn the standard model, but sufficient to make the entire cosmology community stop and reconsider. If this result is confirmed by more data, it will overturn our understanding of the universe's ultimate fate. A dynamically evolving dark energy means the universe's final destiny may be completely different from what we now predict. This number is being watched intently by cosmologists worldwide. The Hubble tension is one of the most serious crises in current cosmology. Measuring the Hubble constant using the cosmic microwave background, approximately 67.4 km per second per megaparsec. Measuring it using Cepheid variable stars and Type Ia supernovae, approximately 73.0 km per second per megaparsec. The gap between these two values has reached approximately 5 to 6 sigma statistically. In 2024, the James Webb Space Telescope's observations of Cepheid variable stars further ruled out the explanation that the discrepancy arose from instrumental systematic error. The Hubble tension is real, and our standard cosmological model is wrong somewhere. Since the James Webb Space Telescope began operations in 2022, it has discovered large numbers of unexpectedly mature galaxies in the early universe, at redshifts above 10, when the universe was less than 500 million years old. Their masses, luminosities, and structures far exceed what the standard cosmological model predicts. If these galaxies are truly as old and developed as they appear, they formed at a rate in the early universe far faster than our current theory permits. This may mean that dark matter's properties differ from our assumptions.